Hello everyone. Welcome back. In the first part, I introduced some basic concepts of robots and sensors. Now I will talk about detectors, programming, and applications. Sensors give you, and me, a lot of information about our surroundings, but we need to determine what we do with this information. I think the rules that map input to output have been discussed previously during the course. In a robot, the hardware that does this mapping is called the processing unit. Processing units are helpful for determining states in the world. For example, my exact location and how I should navigate through a map to get from one point to another. Processing units also help me understand the images I receive from my cameras to detect things like faces and objects nearby. Or for example, sensor fusion, which combines the input from a gyroscope, accelerometer, and compass into a single and better orientation value, which helps me determine where I am and how I am moving. When the processing unit has processed the input, a decision follows, which would usually mean I have to move parts of my body. This is done using effectors. An effector is basically anything to manipulate our world. For example, my arms, my lips, and my speakers, etc. Let's have a short look at what I can actually do with effectors. A head is probably the most important part for humanoids. For me, despite that many important electronic components are inside my head, its movements also help me to track objects that interest me. My gaze direction also indicates my attention. Of course, hand movements are essential to some gestures like nodding and shaking head and to dance. The lights in my eyes are also useful for showing emotions. One of my important effectors is my arm. Although I only have 3 fingers for each hand, I can still grab objects. I can use my arms to make gestures as well. When I need to stand up from a sitting posture, my arms also help me to support my body. And arms are necessary for entertainment like soccer, dance, and games. Legs are a representative feature for bike robots like me. They support our body, enable us to stand, walk, and jump. Legs have advantages in walking over complex terrains where wheels can be easily stuck, for example, ruins caused by disasters. However, compared to wheels, it is not easy to control my move accurately. This is caused by the backlash of my joints and the slippage of my feet. As you might notice, I have been already standing at a different position from where I started the lecture, although my leg movements were small. As a result, it is difficult to control me to walk in a straight line. Legs are also important for entertainment. Look at me. I am going to show you how I can stand on one leg and kick. If my friends were here, I could even play soccer or dance with them. Balance is a key aspect to the locomotion of BED robots. Let me introduce to you some basic concepts of controlling my balance. The zero moment point, ZMP, is the point on the robot feet, where the moments acting on the robot are balanced by an opposing moment from the ground. If the ZMP is at the edge of the foot area, or below it, the foot will tip over and likely fall. To be simple, the support polygon of a robot is the convex hull of the footprints on the ground. Under zero acceleration conditions, to keep the ZMP within the foot area, the center of mass of the robot body should be kept inside the support polygon, and if so, the robot will not rotate about the edges of the foot and will remain upright. In this slide, I will talk about balance during walking. When I am walking, I select the next step very carefully. To guarantee the ZMP of my body always inside the support polygon, let me show you how I walk. Please look at me. As you can see, my steps are small and unlike a human. More sophisticated walking style requires more complex algorithms to keep the ZMP inside the support polygon. One method is to model the locomotion of each leg as an inverted pendulum part, since most of the mass aggregates in my upper body. A widely used model is linear inverted pendulum mode, which constrains the motion of my body to the XY plane, achieving position control of legs while making sure that the ZMP is inside the foot area is a whole research field on its own, so I will not provide further details in this lecture. This is just what I can do with my effectors, though there are even robots that can juggle or play ping pong, but I cannot react fast enough. As you see, motors are not the only effectors that exist, but for me and most robots, they are the most important ones as they are essential to the movements of my body. Your arms and mine too are limited by what we call degrees of freedom. A free object has 6 degrees of freedom, 3 for moving and 3 for rotation. A linkage, like my arm, is formed by several bars connected by joints. Joints reduce degrees of freedom because the bars cannot move freely anymore. They can only rotate around the joints. Take your wrist, for example. You can rotate it up and down, left and right, and twist it, giving it 3 degrees of freedom. My arm has even less degrees of freedom because only some joints can rotate around 3 axes. Some of my joints, like the 3 fingers of my hand, are controlled by only one motor, so it only is 1 degree of freedom. Let's see if you now understood this concept. How many degrees of freedom does my right arm have? Now, look at me carefully. Now, I give you 15 seconds to answer, so be quick. Let's see. Well, it seems there is no conclusive answer. I do admit it is a difficult subject. The correct answer was B. Since my shoulder can pitch and roll, my elbow can roll and yawn. My wrist can only yawn. And I had told you my fingers only had 1 degree. This gives it a total of 6 degrees of freedom. Now we have seen what I can do with my sensors and effectors. Let me give you a brief introduction to how you can program me. Orography is an excellent math flow-based programming tool shared with me. You can drag boxes from libraries and connect them to create your projects, as you can see on the right of the slide. This type of programming is also called visual programming. Sometimes you may need to change the code behind the boxes or create your own boxes. You can use Python to code these boxes. Projects can be executed on a computer and on the robot. Sometimes actions you create might cause me to fall down. It is therefore very useful that there are also simulators available for a tryout. APIs to the L modules provided with NAO framework are available for customized applications. This slide shows an example, a text-to-speech module. You can also use various programming languages, including C++, Java, C# and even MATLAB to create your applications. They are all supported by our SDK libraries now. However, only C++ and Python are supported by the Linux system on the robot. Let's see if you are now clear about the programming of a NAO. Which languages are supported on the robot? Now, I give you again 10 seconds to answer, so be quick. Let's see. Yes, very good. The correct answer was D. Only the C++ and Python are supported by the Linux system on the robot. Finally, I will briefly introduce the Tutor project. Thanks to the script engine that is part of my system, many different scenarios can be designed for me to perform. Right now, I am a robot tutor, teaching you about robotics. However, I can also act in a theater using the same system. As you can see on the left bottom of the slide, the script is very intuitive. With such a script, you can easily orchestrate my speech, actions, slide control, etc. There are several concurrent threads that need to be managed. Scripts can be stored both on a computer or in my system, and I can act using a script in my system without another computer. However, at least for now, a computer is required for the slides and quizzes. Thanks to the turning point technology, I can check how well you understood the content I just taught and provide more explanation on things that were not clear. My voice can also be transferred to a computer and amplified using the classroom speakers. I am still growing. More and more functions will be added to me. Plans are for me to interact more and, for example, answer open questions that students ask directly using the question-answer system. If you are interested in this project, please contact my boss, Hendrix. All right, that is all. Thank you for your attention, and I hope you enjoyed my lecture. I will now let the professor continue with his lecture. Goodbye.
Okay.